resume view and full screen. Okay, so where did I put it? Now I have the question here, so if you don't remember it, I'll write it down for you. So in number 6 here, A1, so I'll draw the diagram. Basically you have different energy levels of isolated mercury atom. So here is n equals 1, and then here is energy level n equals 2, and then n equals 3, and then you'll notice they're getting closer together. Sorry about this, n equals 4. The energy level here is minus 5.5, minus 3.7, minus 1.6, minus 1.2, and they're of course all electron volts. Fine. Define the electron volt. So that's the first question. Do you remember the definition? It's the work or energy the work done when one electron, and then 1 volt, one electron is accelerated through 1 volt. All right. Now, part 2. Oh, this one, it's only 1 mark, but it's so nice. What is the minimum energy required to ionize the electron if it's in this state, okay? So the electron is here. How much energy do you need to ionize it? And ionization is up here. So basically you need this much, okay? Minus 3.7 electron volts means that the electron needs 3.7 electron volts to be freed. So the answer is just 3.7 electron volts. And remember, I told you this before, when a question is 1 mark, it's either going to be given to you in the question, or you just need to multiply a number by another number. Like, it should be something really straightforward, okay? Now the next one is interesting. It says an electron moves between 2 energy levels, which will produce the photon with the longest wavelength. So for example, really there's only really 2 choices, okay? It's either going to be, the answer is either going to be when the electron moves between the biggest gap or the smallest gap, okay? What is the energy for a photon? HF. And what is a formula for F? F is 1 over T, or another one is C over lambda. V equals lambda F. So the H could be V over lambda. If I just do cross multiplication, I get lambda equals HV over E. Okay? If he wants a big lambda, then we need a small energy. So is it going to be jumping from 1 to 2 or 3 to 4? 3 to 4.
That's 1 more?
Yeah. In fact, everything so far has been 1 mark. Sorry, from 4 to 3 or 3 to 4, whatever. Okay. Now, so far it's nice, but that's because they're all 1 marks. Now, the next one here is 4 marks, but it's actually not too difficult. He says an electron okay, so your electron is in state 2 and you would like it to go to state 4, and you would do this by shooting a photon at it. So he wants to know what is the wavelength of the photon required to shoot it, to move the electron from state 2 to state 4. Okay? Do you understand the question? So what do you think we need to do first? Well, first we should find out how much energy you need to go from state 2 to state 4. Okay? So that's the energy in state 4 minus the energy in state 2. The difference between them, 3.7 minus 1.2, so 2.5 electron volts. Okay? Just the difference between the two. Now, we should use joules. So if you take out the formula book and convert it, that works out to be 4 times 10 to the minus 19 joules. So that's the energy. But what do we do next?
What do you find the energy? Just subtract them?
Yeah. Yeah.
Find wavelength.
Now we need to find the wavelength. What formula do we use? Well, in fact, we can use that little one I wrote earlier. Wavelength equals hc over E. Or hv, but v is c here. So, equals hc over E, which works out as 5 times 10 to the minus 7 meters.
This is the second part or one? There's only C, yeah?
This is just C is just C, yeah. Yeah, nice so far, nice so far. D. Light emitted from a discharge tube containing low pressure mercury is analysed by passing it through a diffraction grating of 400 lines per millimetre. The second order diffraction line is at angle 28.5. Calculate the distance between the lines on the diffraction grating, and then there's a second part to it. Okay, so let me draw this here. So D part 1, here is your diffraction grate, and it's, what did I say, 400 lines per millimeter. Okay, and he wants to know how big each gap is. So if you want to write like this, it's 400 lines per 10 to the minus 3 meters. Yeah? So if I multiply by 10 to the 3, I get 400 times 10 to the 3 lines per meter. So there's 4 times 10 to the 5 lines per meter. So in 1 meter, you have this many lines. So he wants to know how big the gap is between each line. So do you remember what to do next? Yeah, just invert it. So that, therefore, that means it's 1 over 4 times 10 to the 5 is the D. And the unit is per meter.
That's the distance between
each individual line, yeah. So that's roughly 2.5 times 10 to the minus, well, exactly 2.5 times 10 to the minus 6 meters. Sorry, what did I write? Oh yeah, sorry. This is per meter, so this is 1 over meter. So of course this must be meter. Right. Now, part 2, you have your little light box, and you have n equals 0, n equals 1, n equals 2, and he says for the n equal 2, the angle is 28.5. We also know the distance. Yeah, we just worked it out there. So let's use our formula. N lambda equals d sine theta. So that means lambda, which is what he wants. Well, he wants the frequency, but lambda equals d sine theta over n, which here would be 2.5, 10 to the minus 6 sine 28.5 over 2. So lambda, that's the lambda. So lambda equals 5.96 times 10 to the minus 7 meters. And then using our C equals F lambda, I can get the F is 5.03 times 10 to the 14 hertz.
Wants the frequency as well?
He wants the actual frequency, not the lambda, yeah.
Is the exam going to be similar to 2017?
I feel it will be. Although, of course, I can't guarantee anything in life. But if you were asking me to place a bet, I'd say yes. Okay. The question is now, can you look here please? This is where the light goes through the grate, okay? And he says this is because this light is a release of a photon because the electron jumped between energy states. And his question is, what energy states did the electrons jump between in order to make this frequency? So what formula can we use? Well, first we should find the energy. So energy equals HF. Do we know the H? We do. And do we know the F? Yeah, so we get the energy equals 3.35 times 10 to the minus 19. Now, the problem is, in our diagram at the start, what are the units? Electron volts, aren't they? So if I change this to electron volts, I get 2.1 electron volts. Okay, now if I go back to the question, we need to see what two states will have a difference of 2.9. And in fact, if you take out your calculator, it turns out to be 2.1. Oh, sorry, 2.1. Is it 2.1? Yeah, 2.1. Did I write 2.1? Yeah, okay, sorry. 2.1. 2 to 3? Yeah, 2 to 3. Okay. Well, actually, it's 3 to 2 if you want to put it that way. If you think about it like this, if the electron goes from state 3 to state 2, has it gained or lost energy? Lost. Because is it getting more or less negative? More. So the energy it lost, what happened to it? Like, it has to go somewhere. Yeah, as a photon. So as going from 3 to 2, you'll make enough energy to make a photon with the frequency that you calculated in the previous question of 5.03 times 10 to the 14 hertz. Is that okay?
So this is the answer for particle.
Sorry, and I should write down. So the answer is from 3 to 2. Right, last, yeah? Last one now. The light from the mercury discharge lamp shines onto a piece of metal with work function. So unsurprising now, we have work function.
Or given?
Given. So you have your piece of metal and the photon hits the metal. Yep.
Yeah.
Oh, well, this one I think is okay. Explain why photons that are released from the 4 to 2 state can release an electron from the surface, but the 3 to 2 can't. So, I mean, that's so easy when you think about it. Like, he's really asking you, if I have a photon and this photon is made when it goes from the 4 to 2 state. It can release an electron. However, if I use a photon that was created when it went from the 3 to 2 state, it can't release an electron. So why do you think that is?
More energy now.
Yeah, I mean, the first one will have more energy than the second one. And how much energy do you need to release an electron? Well, you need, that's what the work function is. So if you did the calculation, this 3.58 blah blah blah, that will turn out to be 2.24 electron volts, okay? And if you go from 4 to 2, back at the diagram, okay, that will make a photon with energy 2.5, whereas this one, what do you think? Would it be, what should it be? It should be less than this, and in fact it is. It's 2, oh yeah, sure, that's the one we did earlier, 2.1 electron volts. So you can see the first case it can release it because it's more than the work function, and in the second case it can't because it's less than the work function, which is the definition of what the work function does. It's how much energy you need to release it. That's actually amazingly generous in my opinion, because that is 3 marks. Okay, so this is a good one once you understand. Once you understand. Now, the last part you could almost guess. It's what is the kinetic energy in this situation. Okay, so what's the formula? It's energy equals the work function plus the kinetic energy. So the kinetic energy equals work function minus E. Did I say that right? Although they wrote it backwards here. Huh? Oh yeah, sorry. Yeah. Taking this over here. Okay, that's fine. Now, what do we know here? Well, we know that this energy here is 2.5, and then we know that this one here is 2.24. I'll convert it to joules in a moment.
No.
Yeah.
So you're talking about the from 4 to 2?
Yeah, it has to be, because there's not enough energy here to release anything.
Oh, we're talking about the one.
Yeah, we're just looking at this one now, yeah. So I get the kinetic energy is 0.26 electron volts. Wow, actually this is kind of, all you're really doing is subtracting between the energy and the work energy. When converted to joules, this is 4.16 times 10 to the minus 20 joules. When you convert this to joules, and that's it. Okay. How long did this take me? About 15 minutes. About this. 20 max, but I wasn't exactly working flat out, you know. What do you think of this one? Would this be one you do in the exam if you saw it? Yeah? What were the others that I recommended for this paper?
2011.
Yeah.